Hello everybody and welcome to our first full week of Physics 1. Ha ha! Whew! Hopefully there are no technical difficulties today. Hopefully nobody has been sent to the wrong stream or is like weirdly learning about like a psychology class right now or something. I mean, if you are, great. Like psychology is a really cool and interesting subject. But hopefully if you're watching this stream right now, you're learning physics. A couple of announcements for the week. First and foremost is a reminder for those of you who are in Professor Tamarow's class and who would like to follow on this lecture. You have a couple of different ways of going about and doing that. The first is you can shoot me an email. And once you sent me that email, just say, hey, Professor Coyne, can you add me to your Brightspace? I will add you as a read-only member to my Brightspace so you can see course announcements, get access to the lecture slides. In addition to that, you can go find the lecture videos on the Brightspace instead of, looking around. Alternatively, and I can't believe I'm saying this in a professional context, you can, sorry, this is making me a little sick. You can like and subscribe to this channel, and don't forget to ring that bell so you'll get notifications whenever I go live. Oh, I feel so dirty. That took a lot out of me, folks. I apologize. But you can, in fact, subscribe to this channel if you'd like to get notifications when I'm going live. You will unfortunately be spammed with my Physics 204 announcements as well. But on the upside, over the semester, I intend to do a few bonus, just like here's some interesting science stuff because we're all trapped at home and we're bored and we can't learn, we can't do anything. So why not learn more stuff throughout the semester, and you'll also get notifications about those. We'll see how it goes. The other announcement is basically that to remember to take a look at, that's a good question. Does the Zoom link for Professor Tamarow's class change every class? I have a student who wasn't able to sit in on Friday. That is an excellent question. I did not think so. I thought it was a recurring meeting, but I will double check with him about that after class. And I'll post an update to the Brightspace. The other thing I wanted to mention was that your first homework assignment is due today. It's up on Sapling Learning, so if you should go take a look. Many of you have already dived in and attempted at least parts of it. I think I saw something like 83 attempts when I checked on Friday, so presumably some more of you have gone in and poked around at that. I'm pretty sure that is due tonight. I'll have to double check for sure, but I'm fairly confident that the way it's set up is that homework will always be due on the Monday each week at 11:59 p.m. For those of you who are a little bit behind, given that the semester start has no doubt been crazy for everyone. And with that being said, let me just say to you folks that I hope you are doing all right. I know that this is a real tough transition. Many of you do not have the benefit of being able to socialize and live on campus in the way that college students deserve to be able to enjoy. I appreciate your willingness to put up with this really strange alternative mode of learning things, and hopefully things will start to get a little bit brighter. And if you have any family on the West Coast who are affected by the fires out there, my thoughts are with you and yours. So did get confirmation in the chat that the homework is in fact due tonight. Thank you very much. All right, with that said, today we are moving on to Chapter 2, where we're going to go from these sort of basic introductory concepts, and we're going to actually learn some physics. These slides are posted to the Brightspace. I haven't quite finished Chapter 2 yet. Unfortunately, I'm going to be a little bit slow to upload all of the slides until I can find a chunk of time to really dedicate to it. And the reason for that is we changed textbooks this semester, as you may recall, and so the order of things are a little different. This led to some problems last week where I was just slightly out of sync with Dr. Tamarow's class, so hopefully that won't happen moving forward. The first half of the Chapter 2 slides are up, however, so you can go to Brightspace if you want to follow along. All right, linear motion. We are talking about linear motion in Chapter 2. This is motion of objects in straight lines. That's what linear means, straight lines, just like the line traveling right down the middle of this slide. Now, to do that, we're going to have to build up a ton of vocabulary. There's another question in the chat that I do want to address real quick before I continue. Does the homework automatically submit tonight, or do you have to click submit somewhere? The way Sapling Learning goes is you have on the sort of individual problems, there's a check answer button. And when you click that check answer button, it either says, check, good, you did it right, congratulations, or hey, this is not quite right, have you maybe considered trying something like this instead? Once you have that check mark, like you have that problem correct, you have credit for that problem. So you don't have to like double submit it. But you do need to make sure that you submit the save answer for all of your problems as you're going through, so that you don't, that you get credit for the work that you did. You can't, just leave the answers in there and expect them to stay. You definitely have to click that button. But there is no submit whole assignment problem to the best of my knowledge. Okay, back to linear motion. We need to talk about a lot of different pieces of vocabulary. Those pieces of vocabulary are going to be new. Some of them are going to be similar to words you use colloquially, and we're going to really need to build precise technical definitions in order to use them to do physics. To that end, we're going to begin by defining the study of kinematics. Kinematics literally means the physics of motion. And so in order to start exploring this, we're going to start by asking some kind of simple questions, and then we're going to develop our vocabulary as answers to those questions. In general, whenever someone or something is moving, there are a few features of that motion that we can describe using words. For example, let's say we were talking on the phone and you were driving down the highway on a road trip. I might ask you things like, where are you right now? Oh, I'm in Indiana, driving through Indianapolis. That is going to lead us to the definition of the physical quantities, position and displacement. I might then ask, well, where are you going? And when do you think you're going to get there? Oh, well, we're headed for St. Louis tonight. And it's probably going to take us a couple of hours. I actually have no idea how long it takes to drive from Indianapolis to St. Louis, but I guess it's actually more than a couple of hours. I chose really bad examples, particularly because like there might be 3 people from the Midwest here or like the Mississippi River Valley. Why didn't I just do like Boston and Providence? I'm from the East Coast. I grew up on Cape Cod. I don't know what I'm doing. Regardless, when I ask you where you're going and how long it's going to take you to get there, that gives you some indication of the direction you're traveling in and say how quickly you're going, whether or not you're speeding down that highway or not. Then I might ask, well, how are you going there? How's the traffic? Is it stop and go? Is it smooth sailing? All of those things have very precise physical quantities that we can define using these simple questions. Once we have those, which we will do predominantly today and on Wednesday, we'll be able to combine them together into some actual physics where we'll be able to predict and calculate the motion of objects in different states of motion. So we're going to start off with the simplest question, position and displacement. Where are you? What is the language we use to describe where things are in physics? And there are 2 important words that are associated with the question, where are you? And that first word is position. An object's position is where it's located. That's pretty simple. This might be a little bit out of the way for your textbook, but we'll get there. So I'm going to, we'll talk about it this way, and then I'll clarify on Wednesday if I have to. Now, there are a couple of caveats to this statement. The first is that an object is big, like it has physical extent. But position is specific. It is a number, usually. So we might say, for example, if I have a ruler, there is an object at a position of 6 inches along that ruler. Now, because objects are big and positions are specific, we need to go through a sort of approximation process. If I have a sort of object like this weird globby person thingy here, it is not useful, usually, as far as physics is concerned, to talk about that position of the whole thing, because the right hand is at one position, the left hand's at another, head's at another, and that just complicates it. So what we do instead is we say that there's a point somewhere within that extended body that represents the sort of center. Later on down the road, we'll realize this point has a very specific name, but we're just thinking about it as the approximate center of where that object is. And so we will always do physics with respect to the position of that central point. Now, for blobby, vaguely humanoid-shaped things, this is a sort of abstract process. But if you imagine I have something like a sphere, well, the center of a sphere is pretty easy to represent as a circle. It's just the point in the middle. So we're always talking about the sort of centroid of things whenever we're talking about an object's position. The second thing that we need to think about is that position is what's called a vector quantity. And vectors may be new to some of you. They may not be new to some of you. But it is a rather complex topic, so we're going to spend a little time unpacking it. And that's basically because position is always measured with respect to something. And that feature there, that we always have a sort of point of reference or a frame of reference for when we're measuring position, is going to lead to this thing being a vector quantity, and we'll explain what that means. But first I'd like to show you what I mean by measuring with respect to something. Okay, the thing to keep in mind about vectors is that they have two components. The first component is the so-called magnitude. That is how much of the vector there is. It's sort of amount. In the case of position, it's literally like the actual number that describes the position. If I say if Boston is 80 miles northeast of Providence, my amount is 80 miles. But vectors are quantities that also have a direction associated with them. So again, note that I said Boston is 80 miles northeast of Providence. 80 miles is the amount, that's the magnitude. Northeast is the associated direction. Perhaps Sasha is sitting 5 feet to the left of Corey. Amount, 5 feet, that's the magnitude. To the left, direction, that's the directional information. To see why this might be problematic, Sasha might be sitting 5 feet to the left of Corey, but Sasha may also be sitting, say, 3 feet to the right of Jamie. Similarly, the ceiling in East Hall Auditorium is about 8 meters above the floor. Note that we're always specifying an amount, the magnitude, and the direction. If the quantity does not have a direction, meaning none of this information is given, it's not important. So for example, a person might weigh 150 pounds. Well, that 150 pounds is just a number. It's not weighs 150 pounds relative to anything, or it doesn't weigh 150 pounds in Oklahoma. It's just 150 pounds. In situations like that, the value is not a vector, it is instead a so-called scalar quantity. So scalars are numbers, vectors are numbers that also have direction associated with them. And that's the important point. All right, let's consider some of that stuff in more detail, and note that statement, that caveat I made about the position. In order to define a vector, we always need a point of reference. We call this generally a coordinate system. You may be familiar from like high school with the Cartesian coordinate system, for example, x, y, and z. These are the standard grid axes that you would see. In our problem statements before, note that I gave a coordinate system or a reference point to all of them. Boston is 80 miles northeast of Providence. It doesn't make sense to just say Boston is 80 miles northeast. Northeast of what? Sasha is sitting 5 feet to the left of what? Of Corey. The ceiling is 8 meters above the floor. This last statement is us setting our reference point in defining a coordinate system. Now, conceptually, I think that's probably easy to understand in language, but mathematically, it's a little bit trickier. To that end, the way we generally define coordinate systems is by setting a so-called origin, meaning the point that we are going to measure everything with respect to. Each of these statements up here is effectively specifying the origin of our coordinate system. Now, mathematically, we have a way of drawing this, and it's specifically with a grid that looks like this. We specify our origin here, and then everything is measured with respect to that. So if I label a point, say, over here, I can use my coordinate system. X is equal to 4 meters, y is equal to 3 meters, and now note that I have a position measured with respect to my origin. This gives us a really nice way. For example, I could come down here. I'm in the way, so instead of trying to hunch over, I'm just going to get small over here. Down here, for example, this is -2, -3. This is 7. Oops, sorry, I got those backwards. Oh, no, yeah, I just read them wrong. My bad. -3, -2. That's better. Here it is 7, -1. Here is -1, 5, and so on. These grids with their origins provide an extremely convenient frame of reference for us to do all of our calculations with. Now, the trick here, though, is that 2 dimensions, as it turns out, is actually kind of hard. We're going to have to build up before we're ready to do 2 or 3 dimensions. So here we have an x direction, and we have a y direction, and there's a z direction that you can't really see that's coming in and out of the page, and those situations are really complex. So instead of doing this, we're going to do this. We're just going to focus on one-dimensional motion for this chapter. Note that we still have an origin. That origin is 0. But our grid has effectively gone away. And so now we're just talking about a number line. If I was standing here, let's say, I am 4 feet to the right of the origin, or 4 meters to the right of the origin. Meanwhile, over here, I am 7 meters to the left of the origin. Note that there is an implicit directionality here. I am either to the right of or to the left of. That's where the direction information comes from our vectors. In our coordinate system, we take those directions, right and left in this case, and we label those as either positive or negative. So what that means is, down here, this is the so-called positive x direction, and this is the negative x direction. So now, if ever I were to see a number, so say, for example, my one person was here, x equals positive 3 meters versus, let's say, this person over here at x equals -5 meters. Green's not going to be a good color. Let's do orange. The magnitude is the number 3 or 5. And in one-dimensional motion, the direction information of our vector is hidden in the sign. It means either left or right. And we're going to be using this throughout this section. Now let's say these are not 2 different people. Let's say this is one person that is walking from one position to another. That means they have gone either from x equals -5 to x equals +3, or vice versa. Turns out we can quantify the amount by which a person or an object's position has changed. And we quantify that change in position with a value called displacement. It is literally just the change in an object's position. Couple of things here. First and foremost, we introduce some symbol here to indicate a change. This triangle-looking thing, that triangle is a so-called it's not so-called, it is a Greek letter. It is specifically the Greek letter delta. Note that it is a capital delta. And it has a very specific meaning. We use it in physics to signify that it is a change. So when we write delta x, what we are saying is that there is a change in the variable x. In this case, this is a change in position, meaning we take our final position and we subtract our initial position. We take where we ended up and we subtract from that where we started. Now note, we use the variable x, and sometimes others like y, z, sometimes r. These variables indicate positions. And so, since position is a vector, whenever you add or subtract vectors, you end up with another vector. So the displacement is also a vector, meaning it has a quantity. Has your position changed relative to your original by have you moved to the left or have you moved to the right? Now, this leads to our first point of real sort of abstract confusion, which is that displacement is a vector with a very specific meaning, and it is very closely related to a concept that you'll be familiar with called distance. But they are not the same quantity, and we're going to have to walk through why that is the case. For now, let's suffice to say that the displacement has a magnitude that's given by the straight line distance between initial and final positions, and the direction is the direction that from initial to final. So for example, let's say we have a little runner over here, and the runner's been running along, and they get to a stop sign, and then they pause here for a second because they're very responsible, so they check to make sure that there are no cars coming, and then they keep running, and they eventually get to here. That means their initial position was this location, and their final position was this location. Note that in both of these cases, I have indicated them relative to a light post. That's because I've specified this as the origin of my coordinate system. The stop sign is my initial position, and the yield sign over here is where I am going to call my final position. It's worth noting that I have indicated my positions as arrows, and arrows are the canonical way that we represent vectors graphically. And the way that we interpret that is the length of the arrow is the magnitude of the vector, and the direction of the arrow, well, surprise, surprise, the direction of the arrow is the direction of the vector. So here, right away, we can see that the final position, x2, is substantially longer than the initial position, x1. And we see that just visibly from the length of these arrows. Now, the displacement vector is this one here. It's going from my initial position to my final position. It has both a magnitude, this length, and a direction from the stop sign towards the yield sign. And so that's how we would visually represent vectors. Now, mathematically, we can give you a sort of example here. Let's say that our origin is 0 meters. The stop sign is at 4 meters, and the yield sign is at, let's say, 15 meters. Calculating my displacement would be x2 minus x1. It is always final minus initial. And so here it would be final 15 meters minus initial 4 meters. As a result, my net displacement is 11 meters. And note that that number is positive. Oops, sorry, come back. Is positive, therefore it is directed to the right as indicated by the arrow here. So that's all well and good. How does this relate to the colloquial word that you all probably would have used to describe that, distance? This is where things get a little bit tricky. Displacement is the difference between two vectors, so it's also a vector. And it's the straight line value between your initial and final position. Meanwhile, displacement, the total length of travel is called distance. Let me show you what I mean by that. Where's my camera control here? Let's say, I'm going to use myself as a diagram here. I'm going to start over here, and I'm going to walk to here. And we're going to call that distance 2 meters. So this is also 2 meters over here. If we were in the classroom, I'd actually be doing it in the classroom, but we're not, so I'm doing it up here on my virtual whiteboard. So I start here, and I start walking. Walking along, walking along, walking along, walking along, and I've stopped. My displacement is 2 meters. I started over there, I ended up here. That is 2 meters displacement. My distance, which is to say how far have I walked, is also 2 meters. Let's consider a different example. Starting here again, and I'm still going to end up at that point, but I'm going to take a different path to get there. I'm going to walk along. I've now traveled 2 meters. I keep walking. I now turn around. I have walked 4 meters. I keep walking, and now I stop. I have walked 6 total meters because I walked past this point and then back. So my distance is 6. But note, my final position is still only 2 meters away from my initial position, so my displacement is still 2. Distance and displacement are two different numbers that depend on slightly different things, even though they quantify very similar quantities. And let's do an actual practical example of that so you can see exactly what I mean and how to combat that. Here we have a problem where an ant crawls north for 4 meters, then turns around and crawls 3 meters south back towards the starting point. We want to know the distance traveled by the ant and what is the ant's displacement. So the first thing we always need to do in these problems is set aside a coordinate system. So I'm going to set my coordinate system as pointing in the north direction is positive, and the south is negative. I'm going to put my initial reference point here, so that's 0 meters, and then I'm going to do 1, 2, 3, 4, 5. And so I've just set up my number line with the origin right over here. So what I'm next going to do for these problems is I'm almost always going to draw something, because when I draw something, that helps me get a physical intuition a little bit about what's going on. So let's say our ant starts at 0 meters. I'm told that it crawls north for 4 meters. So that is the initial path that the ant took. Note that I think we can all agree that the ant has traveled 4 meters in that process because it started at 0 and it went to 4. But now the ant turns around and starts crawling back south. And it goes 1, 2, 3 meters. Now we see how the distance and displacement are related to one another. And actually, there's a good question in the chat. Would it be accurate to characterize the distance as the displacement without the directional component? Not quite. And this example is going to show you exactly why that's the case. Here, the displacement is the difference between the initial location, 0 meters, and the final location, 1 meter. So here, the displacement is actually just 1 meter. And we can read that right off of our number line. But when we ask how far the ant has actually traveled, well, let's track its path. It traveled 1, 2, 3, 4, 5, 6, 7 meters. In fact, in this case, the distance, which is the sort of solving part for part A, is 4 meters plus 3 meters equals 7 meters. As a result, we see that the distance and the displacement are very different here. And this speaks to that question that was asked. Distance is not the magnitude of displacement. Although the quantities are loosely related to one another, they are very different things with very different values. But we'll also note that although I have solved part A here, I have not quite finished part B. Although I know that this total displacement is 1 meter, I need to specify its direction. Here, I have done so by an arrow. If I were to write an answer to a problem on an exam, I would write that displacement is either positive 1 meter, and I'd be very specific to indicate this positive, but this is a little ambiguous. It is generally favorable for you to be explicit when you are explaining what your result is. So plus 1 meter is fine if we are looking at this diagram, but in general, it's kind of ambiguous. Plus 1 meter in what direction? Now, we take north to be the positive direction here, so we might add to this by saying the displacement is plus 1 meter north. It is always better to be more explicit than vague. So it is usually helpful, even if you think it would be redundant to do so, to specify explicitly what the direction is. Hopefully that clarifies a little bit the difference between distance and displacement. Now, we are actually done at this point answering the question, where are you? Where are you is quantified by position, displacement, and distance. Next question is going to be, where are you going? And this is going to be relevant to the physical concepts of speed and velocity. Now, right off the bat, you're actually probably looking at these two words and either saying, I know one of them, or quite possibly, I know both of them. And colloquially, they are the same thing. That's correct. You could have named Keanu Reeves' famous This Bus Can't Go Slower Than However Many Miles an Hour movie. Instead of naming it speed, you probably could have named it velocity too, and most people would not have noticed the difference. But it would have really upset us physicists. The reason being is these two quantities are very closely related, but they are not the same. Now, to see why that is, we're going to talk about two different examples of how to measure these. And the first is so-called average speed. Now, when you ask somebody, like, how fast are you going? Well, or, you know, like, how fast did you get from Boston to Providence? You might say something like, oh, okay, it took me, I don't know, about an hour. And then you could find the average speed by taking the distance divided by the elapsed time. So that ant, for example, that traveled 7 meters of distance, if that ant did so in, say, 7 minutes, or so that's too easy. Let's say 10 minutes. So the ant's average speed, if it took 10 minutes, would be 7 meters divided by 10 minutes, which would be 0.7 meters per minute. You could then convert that to meters per second, miles per hour, kilometers per hour. You could do any sort of unit conversion you like, but broadly speaking, that's the ant's average speed. Note that this is in contrast to the average velocity. Speed is a scalar that depends on your distance. The velocity is a vector, so it depends on the displacement. In this case, the average velocity, note that we use the symbol v to represent velocity. The average velocity is the displacement over the elapsed time. Remember, we see again here this delta symbol. Delta x, that's the change in position, that's the displacement. So that's what we were talking about just a few minutes ago. Delta t is the elapsed time. Delta x is a vector. Delta t is a scalar. So I take a vector, I divide it by a scalar. That's going to give me a vector. Now, this is a real mathematical quantity, and this is what we are going to be using most often. Now, note for the ant, the average velocity would be its displacement 1 meter over that same 10 minutes. So that's 0.1 meters per minute. Note that these are two very different numbers. Average speed and average velocity are not the same, say. Thank you for that catch. Velocity is a vector quantity. Vectors are, of course, vector quantities, but that's something of a tautology. Okay, so we're going to see that speed and velocity are a little bit different, in particular when it comes to averages. So let's see an example of that. We have Jane runs a certain distance along a straight line in an easterly direction. Takes her a certain amount of time. She then turns around and walks halfway back to her starting point in an additional 37 minutes. What's her total displacement? What's her average speed? And what's her average velocity? So we are going to set up our little number line again. Here, Jane is running east to west. So here is 0 km, 0 kilometers. That's where Jane starts. She travels 5.68 kilometers, so a little less than 6K. So we'll do 1, 2, 3, 4, 5, 6. Here's 6 kilometers. And let's see. She then turns around and walks back to halfway between the starting point, halfway back to the starting point in an additional amount of time. So a couple of things here. First and foremost, we're going to do the same drawing that we did before. We'll draw an arrow, then we'll double back. But you'll note that we are not we're told different information here. We're told the distance and we're told the time. So the displacement is actually relatively straightforward. Jane runs 5.68 kilometers. And she goes from her starting point in the easterly direction. Note that we should always define our coordinate system and we should specify what direction is positive. In this case, we're going to define that east is positive, which is what the problem tells us to do, which means west is negative. Generally speaking, when you have an x coordinate, to the right will be positive and to the left will be negative. That is not always true, but that is usually the convention that we choose. Jane then turns around and walks back to halfway back to her starting position. So we're going to have to do a little math here. 5.68 is going to divide that by 2. It's going to give us 2.84. And now the problem wants us to know, what is her displacement, average speed, and average velocity. So I'm going to just annotate my figure a little bit more. I'm going to note that each one of these takes her 30.7 minutes. Now I think I have written down all of the information about this problem here. Now it's worth noting that, again, we can look at this diagram and infer our displacement. It is the vector that goes from your initial position to your final position. So here's my initial position. There's my final position. So that orange arrow is my displacement vector, delta x. And so I think we can probably look and solve for the displacement relatively straightforwardly, since we know that it is just going from our initial position to the halfway from between the starting and ending point. So this is something we can just read right away. It is the final position, x2, minus the initial position, x1. The final position is 2.84. Oop, that might help if I actually wrote in 8. 2.84 kilometers minus the initial position, which is 0 kilometers. As a result, the displacement is just 2.84 km. But what about her distance? Remember, distance is total length traveled. So she traveled 5.68 kilometers in one direction, and then an additional 2.84 in the other. So the distance, which I will call d, will be the initial leg of the journey, 5.68 kilometers, plus the second leg of the journey, 2.84 kilometers. And if I just add those two numbers together, I get 8.52 kilometers. Note again that we see the displacement is very different from the distance. But now that we have this, we can calculate our average speed, which is distance divided by time, and the average velocity, which is the displacement divided by time. In both cases, so that was part A, here's part B, average speed is distance divided by time. The total time, I will note, is 30.7 minutes plus 30.7 minutes. Or 61.4 minutes. And you might normally do some unit conversions here, but we're just going to plug these numbers straight in as they are. So we've got 8.52 kilometers divided by 61.4. And I get 0.139 kilometers per minute. Similarly, the average speed is the displacement divided by time. So that's 2.84 kilometers divided by 61.4 minutes. 2.84 divided by 0.0463 kilometers a minute. These are not convenient So there's a question in the chat, if T1 and T2 are equivalent, why is delta T not equal to 1? T1 and T2 are not 30.7. The way this works is you start the stopwatch at the initial, I guess you can see that green. The initial time is actually T equals 0. And the final time, T2, is the total amount of time that is elapsed when you reach your final location, which that takes 30.7 minutes, then an additional 30.7 minutes. So this is the 61.4 minutes that I was talking about. Therefore, to be very explicit about this, I'll change how I've written this down a little bit. delta t, which is t2 minus t1, is 61.4 minutes minus 0 minutes equals 61.4. Now, the other question in the chat is what's happening here with sig figs, and that's exactly the point I want to bring up with the reflection. The way I've written this here is not super useful in any way, shape, or form. It's not super useful because kilometers per minute is a weird unit, and I've been inconsistent a little bit with how I do my sig figs. If I were to calculate what I have for sig figs here, my position and distance both involve adding numbers with 3 sig figs. 0 here, this can be considered to be a pure number. So it does not affect the number of sig figs. So in the end, my displacement and my position both have 3 sig figs. When I do the calculations for speed, I divide them by the time, which also has 3 sig figs. So my answer should have 3 sig figs in them as well. But I probably don't want to write them this way. What I'd like to do instead is probably convert to a sensible unit. That's probably, the pen's coming apart, meters per second, and then round to 3 sig figs. Note that I do kind of allude to that here. This number has 3 sig figs and this number has 3 sig figs. But I'll leave that as an exercise for you because we are coming to the end of class. Now, I do want to mention something very specific here before we move on and call it a day, is that these quantities, these speeds, are averages. Consider that when you're driving down the highway in the car, you're not talking about, well, at least you don't think about it as your speedometer showing you an average speed. You think of that speedometer as showing you, this is how fast I'm going right now. Well, we solve that problem, the fact that moving objects rarely travel at exactly one speed all the time. They're usually speeding up and slowing down, and the average values don't tell us anything about that. We solve that problem by looking at much smaller increments of time when we are evaluating what the average speed is. So when we talk about an object's average velocity, it's one thing. But when we say an object's velocity, we're actually usually talking about the velocity an object has at a specific moment in time. Now, when you do that, then the magnitude of that object's velocity is now going to be directly related to its so-called instantaneous speed. The issue that average velocity and average speed are 2 different things, that's going to go away when we consider the specific value at a precise moment in time. Now, to do that, we calculate the velocity v using this kind of scary-looking calculus concept from our average velocity. Oh, well, that's an excellent question in the chat that I should actually address before I go on here. For the average velocity in this, yes, we would absolutely need to specify a direction, which would be east in this case. Coming back to this equation here, then we are going to take the so-called limit as t gets very small. Now, this is an algebra-based class, so I don't need you to know how to do the limit. I just need you to understand what this process is trying to represent. It's saying instead of calculating Jane's speed over the whole time scale, well, maybe let's just calculate her speed over half the first run first. And then we'll calculate it over the second. We'll calculate her velocity over the first leg or the second leg. That process is going to give us a better estimate of what Jane's speed is at any given time. To really drive home what I mean by this, let's consider a car that's traveling between 2 stop signs, and we're going to consider 3 different ways to calculate its velocity. So we're going to calculate the velocity in all cases as the displacement, delta x, over the time, delta t. Note that in each one of these cases, the displacement and time is given in the diagram. For this first one, we are considering the average velocity over the whole journey, and our ultimate goal is trying to find the instantaneous velocity, that is to say, the value of the car's velocity at the moment it is passing the fire hydrant in the middle. So at the beginning, we take 60 meters, we divide that by, looks like, did my calculator died. Wonderful. So I'm going to have to do this old school down here. A little silly, stupid phone calculator. 60 meters divided by 8.4150. That is going to give us 7.130 and a whole bunch of other numbers. Note that the sig figs are limited by the numerator here. That's 4. So that's going to be 7.130 meters per second. If I repeat the process down here, note that now I'm considering a smaller displacement in a smaller length of time. So that's 30.00 meters divided by 2.8050. If I plug those in, 30.00 divided by 2.8050, it's going to give us 10.70 meters per second when we round off. And finally, down here, we just consider the displacement right around the actual fire hydrant, which is going to be 6.000 meters divided by a very small 5366 seconds. 6 divided by 0.5366 will be, oops, come back, 11.18 meters per second. Now note that in all of these cases I am calculating a velocity. So there is a positive sign here, which is indicating that the positive sign in this case indicates that the direction is to the right. Now you'll note that all of these values are different. And intuitively, we understand why. Let's just think about how cars work. It comes to a stop, so it's at rest. And so then it starts moving, but it starts moving slowly, and then it speeds up before it starts putting on the brakes and it slows down again. So what's happening here is the car is speeding up, reaching its maximum speed, then slowing down. If we estimate its velocity over the whole distance, we are slowed down by the period of braking and accelerating at the beginning. As we narrow our view to right around the hydrant, we get a value that more accurately represents the car's actual physical velocity as it passes the hydrant. If you continued this process, you made that time interval slower and slower and slower, smaller and smaller and smaller, eventually you do arrive at precisely the instantaneous velocity of the car, which is what its speedometer would be showing as it passes the hydrant. This is what I mean by taking the limit. I take a large time in a large displacement, and I gradually make those both smaller until I get something that is very close to the true value instantaneously at the moment it passes the point of interest. There's a question in the chat of if this process is the integral. This is actually more closely related to the calculus process of taking the derivative, which is not something you'll have to worry about in this class. So if you're rusty on calculus or have never taken it, don't worry. This is as close as we're ever going to get. Ooh, so I almost knock over my green screen. Okay, with that said, we are going to be done for the day. Next class, we're going to talk about how to visualize mathematical behavior and how to visualize velocity, and this will give us a better understanding of the difference between instantaneous velocity here and the so-called average velocity. and we'll talk about that next time, and then we'll move on to talk about things like acceleration and so on. In the meantime, if you have any questions or comments, I'm running upstairs to my office for office hours now. You can just pop in. For those of you who are making one-on-one scheduled appointments during my Monday, Wednesday, Friday office hours, please do keep in mind that these are walk-in office hours, so people may come in and interrupt us. If you really want a one-on-one meeting, make the appointment for the afternoon. Otherwise, folks, have a great day. I will see you on Wednesday, and don't forget to take a look at your homework. It is due tonight by 11:59 p.m. Have a great day, and I will see you Wednesday.